Hello, everyone. The Space Channel is with you. Today, because of Russia's ongoing aggression, a nuclear catastrophe is one of the potential threats. Russia constantly intimidates us with the launch of missiles tipped with nuclear warheads and with terrorist attacks on nuclear power plants. And although these threats fortunately have not yet materialized, we must be ready to act if a large-scale nuclear incident really occurs. Who knows what is in the heads of those mad Russians? Therefore, we will now give answers to several important questions. And the first of them, what danger zones will arise in the event of damage to nuclear power plants or waste storage facilities, as well as in nuclear explosions? Radiation hazard is a threat that evokes the greatest anxiety in society because of its scale and unpredictability. A wary attitude toward radiation accidents is not an exaggeration. In just a little more than 100 years since the discovery of radioactivity, humanity has, intentionally or accidentally, caused hundreds of large-scale nuclear catastrophes, among them atomic bombings, accidents at nuclear reactors, and leaks of radioactive substances. Moreover, a serious threat is posed not only by the immediate impact of nuclear incidents, but also by their long-term consequences, which can persist for decades and even centuries owing to radioactive contamination of the territory. The first nuclear catastrophe that caused the deaths of tens of thousands of people was the atomic bombing of the Japanese city of Hiroshima on the 6th of August, 1945. That explosion, with a yield of 15 kilotons in TNT equivalent, created several lethal zones differing in size and dominant damaging factor. The bomb detonated at an altitude of 600 meters. Beneath it, within a radius of 500 meters from the epicenter, a zone of complete annihilation formed. The simultaneous action of light radiation, an extremely high-pressure blast wave, and a stream of radioactive radiation incinerated all living things and razed every building except for seismically resistant concrete structures, which remained standing but were severely damaged. Within a radius of 500 to 2,000 meters from the epicenter lay a zone with minimal chances of survival. Radioactive radiation contaminated the territory, the blast wave inflicted massive destruction, and the light and thermal radiation, though it did not burn living organisms to ashes, caused very severe burns. Due to the intense heat, a fire broke out, grew into a firestorm, and destroyed all the surrounding buildings. Only at distances greater than 2,000 meters from the epicenter did the destructive effect begin to diminish. However, the radioactive dust lifted into the air, entered the clouds, was carried by wind currents, and fell with the rain. As a result, to the northwest of Hiroshima, an area with a radius of up to 19 kilometers was contaminated, later causing radiation sickness in people and animals. Subsequent tests of nuclear and thermonuclear weapons showed that the affected zone increases less than proportionally to the growth of bomb yield. Nevertheless, ballistic missiles that carry numerous warheads of relatively moderate yield can create a vast field of nuclear explosions, where survival would be possible only in an underground concrete shelter, and radioactive contamination could spread tens or even hundreds of kilometers. Unlike nuclear explosions, nuclear accidents at power plants and industrial sites are not accompanied by such massive destruction. Their main danger lies in the sudden release of a cloud of radioactive particles or the entry of radioactively contaminated water into freshwater bodies. The largest man-made catastrophe at a nuclear facility was the accident at the Chernobyl nuclear power plant. The scale of that disaster was greatly increased by the opening of the reactor's active zone as a result of a non-nuclear explosion. After the accident, two exclusion zones were created: a 10-kilometer zone with maximum levels of radioactive contamination and a 30-kilometer zone from which the entire population had to be evacuated. Subsequently, these dimensions became standard in guidelines devoted to dealing with the consequences of large-scale radiation accidents at industrial and energy facilities. In particular, they are mentioned in materials of the U.S. Nuclear Regulatory Commission. After the 2011 nuclear accident at the plant in Japan's Fukushima prefecture, A 20-kilometer exclusion zone was established around the station. However, thanks to early warning signals, the population sheltering during the accident, and the gradual decontamination of the area afterward, the consequences proved less critical than in the case of the Chernobyl MPP. How serious will territorial contamination be, and how quickly will the radiation background decrease? Because nuclear catastrophes have occurred with a certain regularity and frequency, scientists have managed to gather statistics that allow them to forecast the area of contaminated territories and the degree of their radioactive pollution. Factors that markedly increase the size of the radiation-affected regions include the release of radioactive byproducts from an accident into the open air, their spread by wind, and their deposition on the ground during rainy or snowy weather. Most often, isotopes, nuclides of the same chemical element that have different numbers of neutrons and therefore different mass numbers and atomic masses, uranium-235 and plutonium-239, are used in military and civilian nuclear reactions. Their fission produces characteristic isotopes that, during a nuclear incident, freely escape and contaminate the surrounding territory. These include iodine-131, strontium-90, and cesium-137. The danger of these isotopes lies in their radioactivity and in their ability to replace the natural, non-radioactive iodine, strontium, and calcium in the bones, tissues, and organs of humans. The isotope iodine-131 has a half-life of 8 days and causes radioactive contamination of the shortest duration. However, it readily accumulates in the human thyroid gland and, as a source of alpha and beta radiation, can cause mutations and cell death. Prophylaxis against the accumulation of iodine-131 is the use of potassium iodide tablets. These tablets should be taken only in the event of radioactive contamination and an appropriate emergency announcement, because their unjustified use can cause severe harm to health. The isotope strontium-90 has a half-life of almost 29 years. It is dangerous because it can accumulate in the bones, where irradiating the bone marrow leads to chronic radiation sickness and osteosarcoma. The third isotope, cesium-137, creates the highest level of radioactive contamination during man-made accidents. It has a slightly longer half-life, approximately 30 years, and accumulates in soft tissues in the liver, causing damage to these tissues by ionizing radiation. Besides the isotopes mentioned above, another insidious isotope exists, whose contamination is only now gathering momentum. This process can be observed in the Chernobyl exclusion zone. Plutonium-241, ejected from the destroyed reactor unit, has over time, through radioactive decay, turned into americium-241. This isotope is toxic, possesses powerful intrinsic alpha radiation, and can migrate rapidly through soil layers. Its treachery lies in its huge half-life, almost 433 years. According to the hypotheses of some scientists, it may be more hazardous to the human body than strontium-90. The degree to which territories become contaminated by radioactive elements varies in intensity from incident to incident. Yet the greatest danger is the chaotic distribution of contamination spots in which radioisotopes can continue to decay for a very long time. If the reduction of the radiation background from radionuclides dispersed as fine particles proceeds rather slowly because of the long half-lives of the isotopes, the diminution of radioactive radiation intensity from the direct action of nuclear and thermonuclear explosions occurs quite rapidly. Radiation safety specialists derive the 7-to-10 rule, which enables the determination of how the radiation background will diminish over time. The 7-10 rule states that each 7-fold increase in time after detonation corresponds to a 10-fold decrease in radiation power. In other words, when the amount of time is multiplied by 7, the radiation level is divided by 10. Thus, 7 hours after a nuclear explosion, the intensity of radiation will have fallen 10-fold. Features of using respirators in a radiation-contaminated zone. Respirators and gas masks are an effective means of preventing radioactive dust from entering the body. Yet in documentary and feature films, particularly in the series Chernobyl, one can see that some personnel in the radiation accident zone neglect to wear respirators. Why does this happen? To understand it, one need only recall the COVID-19 pandemic and the people who refused to wear masks. Their main argument was that the masks were uncomfortable and made breathing difficult. When such arguments are advanced as an excuse not to put on a mask for a trip to the shop, that is mere laziness and disregard for one's own life and health. But in the case of prolonged wearing of respirators and gas masks while performing heavy physical labor in a radioactive zone, these arguments are valid. Currently, the risk of radioactive contamination is outweighed by the risk of losing consciousness due to a shortage of oxygen in the air that has passed through dense filtering elements. Moreover, in a long-term radiation-contaminated zone with a large number of people, it is impossible to supply everyone with personal protective equipment in sufficient quantities to ensure that it is available for all and can be replaced at the recommended intervals. After all, a respirator must be replaced after 2 hours of use in a heavily contaminated zone, and a gas mask filter after 3 or 4 hours. According to the recollections of one of the Chernobyl disaster liquidators who carried out tasks in an evacuated settlement, a significant amount of condensate accumulated in the respirator during work, so it had to be periodically removed and the liquid poured out. While he was breathing in the respirator, the valves turned beet-colored. After a specific time, the respirators had to be changed, yet work in them remained arduous. To sum up, regardless of the difficulty in breathing and working in a respirator, it must be worn without fail in a radiation-contaminated zone, as the entry of radionuclides into the human body through the respiratory tract can lead to extremely severe health consequences. Additionally, it is essential to wear protective clothing to prevent skin contact with radioactive substances. After evacuation, it is essential to change clothes and take a shower to minimize the risk of internal irradiation. Which products can be consumed after a nuclear explosion or an accident at a nuclear power plant? Civilian guidelines for staying in a radiation-contaminated zone emphasize that, in order to avoid additional radiation exposure, only clean food and drinking water should be consumed. But how realistic is it to obtain them in the accident zone? It depends on whether the big land, the clean zone, remains intact beyond the contaminated territory. If so, then one should consume only those products and drink only that water that has just been delivered into the contaminated zone from the clean territory. Consume them immediately and avoid stockpiling. If it proves impossible to deliver provisions regularly, then reserves of clean food and water must be stored in sealed containers in areas with minimal radiation levels. Additionally, the provisions can be placed in metal containers to shield them from alpha and beta radiation. Products and water that should definitely not be consumed in a radiation-contaminated zone include mushrooms and forest berries, as well as vegetables and fruit from kitchen gardens and orchard trees. Additionally, meat from animals that have grazed on pastures and water from lakes, streams, and wells should be avoided. In fact, everything that was exposed to the open environment at the time of a nuclear accident or explosion becomes radioactively contaminated within the affected zone. After leaving a radiation-affected area, it is essential to monitor your health. The first signs of exposure may appear as nausea, headache, or weakness. If these symptoms occur, seek medical help immediately. To remove toxins and radionuclides from the body, sorbents such as activated charcoal or enteros gel are recommended. They help carry toxins out. Chelating agents, e.g. unithiol, bind heavy metals and radionuclides. Iodine preparations, such as potassium iodide, block the uptake of radioactive iodine, while antioxidants, including vitamins C and E, protect cells. Potassium orotate can be taken to support metabolism. During a radiation accident, iodine prophylaxis protects the thyroid from radioactive iodine. Potassium iodide should be taken as soon as an official danger notice is issued. Adults, 125 milligrams. Children aged 3 to 12 years, 62.5 milligrams. Infants, 16 milligrams. One dose is usually enough. Repeat only on medical advice. Realistic rules for surviving in a nuclear disaster zone. In all, dozens of detailed guides have been written on surviving during and after nuclear explosions and man-made catastrophes with radioactive releases. Their drawback is that they focus on individual behavior, yet an atomic accident is certainly not something a person can cope with alone. Therefore, the most crucial advice is to heed alarms and official notices from the authorities whenever any kind of nuclear threat arises. In a nuclear incident, 3 broad scenarios are possible: 2 pessimistic, 1 optimistic. First pessimistic scenario. You find yourself at the epicenter of the catastrophe, with a high likelihood of dying instantly in a flash or later from radiation sickness. Second pessimistic scenario is an all-out nuclear apocalypse. You survive in a shelter, but soon discover that state institutions and production capacity have been destroyed. Once clean food and medicines run out, you must breathe tainted air, drink radioactive water, and eat contaminated food. The quality of life for your generation will plummet, and whether the next generation can live in a cleaner world will depend on environmental levels of strontium-90 and cesium-137. Optimistic scenario. The nuclear accident is local, like Chernobyl or the Fukushima event in Japan. Here, the main task is to follow official instructions and leave the contaminated zone as soon as possible. You will almost certainly not have a dosimeter or isotope detector to verify that your home, water, and food remain uncontaminated. The largest one-time civilian evacuation from a radiation accident zone was the removal of 47,500 residents of Pripyat on 27 to 28 April 1986. Despite articles claiming the operation was irresponsible because it gathered people at assembly points during peak radiation, no convincing evidence of increased radiation-related illness among evacuees has been found. In 2005, the WHO's Chernobyl Forum report recorded only 40 confirmed deaths directly attributable to radiation in the area around the plant. Dr. Barton Bennett, a radiation effects specialist and forum co-chair, stated that no profound negative effects were discovered in people who were not disaster liquidators, but were in the vicinity at the time. Thus, rapid evacuation, rather than sheltering in place with supplies, proved to be the more justified approach. There are no universal survival scripts for nuclear catastrophes. The key asset is information, early warning of the incident, and knowledge of how to quit the danger zone as fast as possible. The long-term future of radiation-tainted territories will depend on advances in technologies that immobilize radionuclides and decontaminate land without waiting for multi-decade half-lives to pass.